Okay, hopefully
Yeah.
you can see my screen okay.
Yes, yes, Professor, we can go
Okay,
ahead.
so this presentation is, well, somebody stole my line earlier. Something completely different, a la Monty Python. This is about spatial decision support for environmental analysis and planning. And I'm going to include some recent examples from the ecosystem management decision support system, which I've been working on for a long time. And is the volume okay? Okay,
Yes,
good.
yes.
Okay, thank you. So just some basics about this technology. EMDS is a spatial decision support system that's been around for a long time. We started into it actually even earlier than that, designing it in 1994, and we've just released version 8. The basics of it in the 25-cent version is that it's a general application framework for designing and implementing knowledge-based decision support applications for environmental analysis and planning. And the framework idea is important. This is not your father's decision support technology that is built to solve a very particular problem. It's a technology for building decision support systems. It integrates geographic information system technology as well as a variety of knowledge-based reasoning, decision modeling technologies to provide decision support, basically for an adaptive management process. I was going to hang on one sec. I meant to time myself. I'm not going to go through all these examples. I just put this up here as a sort of reminder. There have been a lot of applications developed for many different kinds of problems at many different scales around the world using this technology. It's going back to the late 90s. The main thing I want to draw your attention to is at the bottom here. There's a Wikipedia site that has virtually all the peer-reviewed publications that have been written about EMDS from the beginning. You can find it on Wikipedia. If you just type in EMDS, you can pull it up pretty easily. There you can find all the publications classified by the kinds of problems and all the publications available, mostly as PDFs. So a little bit about architecture. EMDS is a GIS-based technology, like I said, and it's been based originally since 2002 on ESRI's ArcMap, which is a commercial system. So recently we are about to release now open source versions, and one I'll point out because it's popular in Europe is QGIS, and there's some other ones. And we're also quite soon coming out with a web-based enterprise edition, probably sometime by the middle of this year. This will run on platforms like Amazon and Azure, Amazon and Microsoft Azure. Just another couple of quick things. I'm not going to spend much time here, but it's been developed originally for a long time now, up till now, as a desktop system that relies upon a variety of different spatial database systems that are shown here. And again, we're moving to cloud-based services that will be able to handle Azure or AWS application environments. Now, this is sort of the core of what I wanted to talk about. EMDS is a rather large, complex system. There's a core which manages the interoperability of a variety of analytical engines, and that's what I have here. So I'm going to just briefly review these. The first and foremost, which has been around forever in our technology, is a system called NetWeaver, which uses logic-based processing, in fact, fuzzy logic in particular, to support the design of very large, complex, and abstract models. And what I mean by that is models that can address questions about sustainability or ecological integrity or ecological resilience, things like that. These are large, very multifaceted problems that are difficult to solve or evaluate with sort of classical statistical and quantitative methods. The next one, which is very complementary, so the first one, one last point. First one is about answering the question, what is the state of a system? And one of the beauties of logic, and why we've used it forever, is that if I can reason about it, I can model it. Now, the next part is a system called CDP, which stands for Criterion Decision Plus. This uses classical multi-criteria decision analysis, and we use that as a complement to the logic-based processing to support strategic and tactical, excuse me, strategic and tactical planning. And then we have two more recent additions that provide other ways of reasoning about information. VisiRule is a prologue-based decision tree technology. We built that in as a complement to the CDP because CDP uses classical multiple criteria decision analysis, which is intrinsically linear. So at some point, the complexity of problems that technology breaks down. However, VisiRule allows you to build extremely complex reasoning to support tactical, complex tactical decision problems. And then the last one is Genie. This is Genie implements Bayesian networks, so it's sort of another alternative to logic-based reasoning based upon probabilistic reasoning. So again, they sort of complement each other. And you may be wondering, why do we have all these models? Well, I'm going to get to that in a little bit, but I'm going to skip over that slide. Part of what's important to the framework concept and the ability to build very general models is the availability of scripting tools, which we have built into EMDS. So it makes use of R, Java, Python, and C#. And in the next slide or two, we're going to look at how that fits into a workflow concept. And this is really important for generality. Systems that can be designed to evaluate a very wide array of problems. And so the workflows is an important concept in terms of this idea of generality. EMDS itself is built on the open source Windows Workflow Foundation. This basically supports task sequencing of analytical processes through a variety of mechanisms like flowcharts, sequential diagrams, state machines, and so on. We started out by leveraging a system called Trident. This was an open source workflow solution and editor built on the Windows Workflow Foundation, which was originally developed by NOAA, so the National Oceanic and Atmospheric Administration, the US government. And we've basically borrowed several of the user interface components and provenance structures from Trident, but we've built that out into a later, more modern edition based upon Wexflow, which some of you may be familiar with. This is a very popular workflow environment for basically sequencing a series of tasks in very complex processing, and in our case, geoprocessing. We might also be adding KNIME because it's would be an easy extension, both of which can handle the primary point of these is to be able to handle data processing and statistics with things like R in spatial decision support applications. And I'm going to talk about some more specific examples in a little bit. I have three that I'm going to go through very briefly. The first is an example of evaluating landscape integrity, which is the simplest one, because this one is simply focused on a logic-based approach to interpreting landscape integrity. The next one is a bit more complicated. This is an application looking at landscape resilience. Here, it starts with an analysis of what is the state of ecosystem resilience, and then those results are summarized and passed to a decision model. And the key thing about this one is that this is where I can illustrate a little bit the power of workflows in solving complex problems. And then the last one, if I have time, the last one, if I have time, is a more sort of prototypical case where I kind of lay out the argument for what's the rationale, what's the value of combining all of these analytical technologies under one roof. And this is sort of the case for engine interoperability. So the first example is from the US National Forest System. This is has been providing a national assessment of forest ecosystem integrity. This actually dates all the way back to about 2011 when we started on this work, and we're still at it. This evaluation of integrity covers 19,000 ecological units, which represent all of the national forests and grasslands of the continental U.S. And we've added recently Alaska into the mix, so we've covered most of the United States territory in terms of national forest lands. To give you sort of an idea of the scope here, this is, as I mentioned, it's strictly a logic-based interpretation and synthesis of information. So it's again addressing the question, what is the integrity of these systems? So it's assessing ecological state. It draws upon 10 very large, very well-vetted, highly developed national databases for this analysis. And that represents a huge amount of data. It's approximately $80 million worth of data there. These data sets are updated anywhere from 1 to 3 years. But we also draw upon another database system called FACS. FACS is basically the Forest Service's data repository for all the management activities that take place on all Forest Service land. And we draw upon that and update these large national data sets to, at the end, produce an annual report to the US Congress, in particular on the agency's performance with ecological restoration. So the focus here is very much about outcomes instead of counting widgets, which has been sort of since the early 2000s a major focus of decision support systems. Here is a very simplified overview of the logic of the terrestrial condition assessment. At the top is sort of the overall goal, which is to evaluate ecological integrity in this case. And it's broken down into 2 major categories of disturbance agents and stressors and vegetation condition. And the stressors are broken out further into biotic and abiotic agents. And then down below here, the square box, the rectangular boxes these are the primary indicators that feed this model. Now, there's only about 12 there, but the data that feeds these is massive. And so there's about actually 40 data inputs total that go into this model to evaluate integrity. And I'm going to cut to the chase here. And I have to tell you that I'm going to show you one map. There's about 40 maps. This is the overall top level result. And the way to think about these models is it's a bit like peeling an onion. The one you're seeing here is the topmost level, which is evaluating integrity. And this breaks down into maps that demonstrate the evaluation of stressors, and another map that evaluates ecological condition, and down and down and down. So there's layers and layers of maps here. I'm just showing you the one because of the time frame. The color coding is very simple. Again, it's about ecological integrity. And what you see here is the map symbolized from very poor to very good outcomes with respect to integrity. And it's important to understand this is logic-based, but it's fuzzy logic-based. So these are continuous metrics underneath, which is a powerful feature for being able to, when we get to performance analysis, we can evaluate data at a fairly precise level. Okay, the next example is Lake Tahoe Forest Ecosystem Resilience Assessment. And for those of you who are not that familiar with US geography, Lake Tahoe, as Will know very well, is an iconic lake in the Sierra Nevada range of California. And the area that is covered in the study is a major segment of that, representing about 20,000 hectares. So a much smaller problem spatially than the first one. But this one, the focus is on resilience assessment. What I mean by that is what's the ecological, how is the system functioning over time? And this particular project is looking at projecting the performance of resilience over a 100-year time frame. Now, the interesting thing here is EMDS was built originally, going back decades now, as a spatial decision support system. This one's a little different because instead of a spatial problem, this one is a time series. In this project, the team looked at 5 alternative management scenarios, which I'll show you in a second. It starts with a logic-based assessment, as I mentioned a minute ago, but then the information flows into strategic decision models to compare performance of scenarios over time. Now, really quickly, I won't spend a lot of time here, but the major scenarios that are covered are shown here. First one is fire suppression only. Scenarios 2 and 3 are basically alternatives using mechanical thinning to modify ecosystem structure and composition, different levels of thinning operations. And scenarios 4 and 5 are looking at fire-based approaches using prescribed fire to modify the environment. And again, scenario 4 is light. Scenario 5 is the intensive version. I can't go into all the modeling because they're huge, but this is the core decision model at the end that processes all the information that comes out of the logic model. This one is looking fairly simple. It's evaluating the ecosystem resilience of environmental quality, which is broken out, as you can see, into these different categories. We'll go through those. So there's 5 basic inputs here, but the amount of data that's being fed here is massive. So the logic, we're using the logic on the front end to distill a lot of information and pass it into what looks like a fairly simple little decision model. Workflows were really important in this. And so this is the workflow portion of the conversation. The overall analysis required 200 logic model runs. That's looking at 4 resilience topics, which feed the decision model. The 5 scenarios evaluated 10 time steps, you get 200 model runs. If you had to do that manually, it's a huge job and it would take weeks, or at least several days and maybe a couple of weeks. The 10 decision model runs are basically taking, as I mentioned, all the outputs distilled down from the logic and running it for 10 times across the 5 scenarios. The beauty of the workflows, and this is why they are so powerful in complex spatial decision support problems, or in this case, a temporal version. We coded all this, and instead of taking days and days and days to compute the outcomes of the analyses, you push the button, one button push, and it generates all the results. And I'm going to show you again a very distilled version. This is like the comment earlier about peeling an onion. This is the topmost level of the decision model, which is looking at the trajectory of resilience performance over the 5 scenarios for Lake Tahoe. And my 5 scenarios over here, just as a reminder, the first 4 are dealing with fire suppression or different way. That's mechanical treatment. Sorry, mechanical treatment, heavier mechanical treatment, and light prescribed fire. Number 5 is the more extreme application of prescribed fire. The main message out of this whole process, after distilling thousands and thousands of data inputs, is that the more intensive prescribed fire scenario stands out sort of head and shoulders above the other 4. The other 4, as you can see, are kind of clustered in terms of their performance over the 100-year time frame. Now, this is the last one, and I'll try to go through this quick so I stay on time here. I put together an example, and it's sort of hypothetical, but this is an example of why would you want to use all of these different kinds of modeling systems in an application. So this is my sort of prototype of something like that. You might imagine or have a problem that involves evaluating ecosystem restoration. So in this example, we're starting out with the SMILE engine is the Bayesian network engine. And we might start out by using this to assess the population viability of a number of keystone species. So those are looking at a few fairly narrow, well-defined problems for which Bayesian engines work great. But our bigger question is ecosystem restoration. So the outputs from those models can feed into a much larger, broader, abstract model dealing with ecosystem integrity. And here, so the Bayesian outputs are fed into that thing. And now we're looking at an overall evaluation of ecosystem integrity, which is taking account of more finer scale modeling coming out of the population viability studies. Now, at this point, all we've answered the question, the question we've answered is, what is the state of the system? And the next problem is, okay, now we know that, what do we do about it? So this is where the CDP engine is invoked to support a strategic decision model to identify high priority places on a landscape. And I'll do this quickly. The last little bit is we've decided where are the high priority places. The final question in a sort of mid-scale strategic analysis is, what are the high priority activities that would make sense to do in those places that you identified? And this is where the visit rule model comes in. So that's my explanation of sort of why all these models sort of make sense to pull together into one integrated system. And the core EMDS basically manages the interoperability of all that. And the last point is going back to the workflow idea. The scripting tools are off here on the side, but they're shown as being inserted to support summarization and transformation of information to get me from one analytical phase to the next. So that's kind of my simplified scheme. And with that, I'll pause pretty much right on time. I'll take any questions if we have time, or if there's interested, and there's a note there how to contact me if you want. Thank you.
Yeah, thank you, Professor Reynolds. Thank you. Yeah, any questions from anyone from the audience?
Yeah, hey, I have one actually. Hey, Keith, thanks for the presentation. That's fascinating work. Wow.
Thank you.
My question involves a little bit of navel gazing as a Californian, right? You can probably guess where my question is going to go. For those of you who are not familiar with the California fire scene, last year we had one of the most violent fire seasons, one of the most voracious fire seasons on record. And it really, fire is a common occurrence in California. It's expected, but the extent of the fires last year were off the charts. And you can kind of hear where my question is there. Keith, how would you feel your models fared in, what happens in a situation like that in your, not merely in your ability to model, but in the efficacy of the model moving forward? Is that treated as an outlier situation, or is that now increasingly being recognized in the modeling as a kind of new normal that you have to expand in order to measure?
Yeah, really, that's a good question. Well, it's hard to give you a really straight answer on that. We have done actually in the Pacific Northwest a number of years ago, which we never published it, but we did some modeling of wildfire for the Pacific Northwest to look at how to prioritize things like fuel treatments for reducing hazard, things like that. And those models were actually fairly effective at identifying outliers. We built into it specifically. We were looking at fire behavior and using a ensemble of ways of evaluating it. And one of the things we included was a model from the Missoula Fire Lab. And we had a probabilistic version, and then we also included an extreme version where the behavior was based upon 95%, what's the right one? 95th percentile of fire behavior. And it worked out pretty well in terms of painting a picture that fit the fire disaster in the Northwest last year, by the way. So it identified places that, well, if you had a fire there, man, you're going to have a big problem. And it did pretty well at that. So it kind of depends. The probabilistic one, when you look at long fire history, can be a little bit misleading. But when you include the 95th percentile fire events and factor that in, you get a decent picture. But that help.
That's just fascinating work. It's really interesting. We're certainly going to need it. So thanks for developing the model, or models,
Yeah.
I should say.
I should, well, since you're in California, the stuff that I was showing you from Lake Tahoe is being broadened out to that. There's a much larger region. I think it's the American River Valley or something like that, but it's more like a 2 million acre area. And so they're looking at it, basically adapting what we did there in Lake Tahoe to a much larger area. So it's been used extensively in California for the terrestrial condition assessment I was pointing out earlier. California looks kind of bad. And it's all driven, I didn't point that out when I was showing you the figures, but the East and the West look wildly different. And the problems in the Western United States are driven by climate change, fire, insects and disease, and they all interact. And the whole Western United States lights up. It's an ugly looking picture. We showed that to we showed that to the national office, and they said, "Don't show that to people."
We're really looking at, as you're suggesting, we're really looking at increasing cascading events, right? And it looks like the modeling you're developing is going to help us considerably understand how those feedback loops are being, we're behind in the measurement of feedback loops, but it looks like your model is beginning to address some of those feedback loops, especially if it's, as you're saying, it's showing a great deal of promise even in the outlier, situations like last year.
Well, in terms of the feedback stuff, in the spatial in the pure excuse me, in the pure spatial implementation, there's not really any feedback, so it's a point in time assessment. But the example I was showing you from Lake Tahoe, that was a time series where they were running vegetation simulators for 100 years, and there you can build in. There's where the feedbacks get built in and accounted for.
Yeah, we're missing that in the ocean, as you probably picked up from what I said. Yeah.
Thank you. Thank you.
Yeah. Thanks. Good questions. Appreciate it.